This video is going to be a review of the calorimetry experiment, where the overall goal of activity 1 was to determine the heat capacity of the calorimeter so that you could characterize the enthalpy per mole of solution for a calcium chloride sample and an ammonium chloride sample in activities 2 and 3 respectively. So I'm going to highlight the math that was associated for the analysis, but I'll also indicate tidbits of the procedure as we go through, where you obtained 50-gram samples of hot and cold water, where you actually measured volume. But by this point in the semester, you should have a thorough understanding of how to convert volume to mass by the density, even though I haven't gone through that as a written process here. A new piece of information is the specific heat of water. So specific heat is represented by S here, lowercase s, and the standard value for this is 4.184 joules per gram degrees Celsius with relation to water. So this is a standard value that you can look up from a table. In terms of the experiment, you added 50 milliliters of your cold water to your calorimeter and allowed it to equilibrate so that you could take a look at the temperature before you began the experiment. And so for example, that's going to be 24.0 degrees Celsius. While that was equilibrating, you measured and you warmed some water so that it was between 75 and 80 degrees Celsius. And for the sake of our example that we're going to be working through, that temperature was 78 degrees Celsius. And so in terms of the experiment, you added the hot water very quickly to the cold water. And over the course of 10 minutes, you measured the temperature that you observed in your calorimeter at 1-minute intervals. And you were able to generate a plot to illustrate that correlation. And from that plot, you were able to generate a trend line, get a sense of the equation for that trend line, and also take a look at the linear regression or R-squared to get a sense of how good that correlation was. So at this point, we have all of the information that we need in order to determine what we want, which is the heat capacity of that calorimeter, so that you can use that information downstream to analyze the enthalpy per mole of solution for calcium chloride and ammonium chloride. I'm going to be writing equations in red so that you can follow what it is I'm working on. So the first step to get to that heat capacity of the calorimeter is to look at the change in heat for each of our water samples, the hot and cold. And so the general equation for the change in heat is equal to the specific heat times the change in temperature times the mass of your sample. So in this case, we're looking at water. And so we can see that we have the specific heat of water, which is our standard value. We also have the mass for each of our water samples of 50 grams. But at this point, we're not really familiar with how we're going to get that change in temperature. You might be wondering, well, I have two temperatures here, but you'll recall that this temperature of 24.0 degrees Celsius is representing the temperature of water before the experiment. And this temperature for the hot water is representing the hot water before you added it to the cold water. So in other words, you want to think of these as initial temperatures. The way that we calculate delta T, or the change in temperature, is by taking the final temperature and subtracting the initial temperature. So we already said that we have this initial temperature, but how are we going to determine this final temperature? We're going to be using the plot to the left to determine the temperature at time equal to 0, which on your data sheet was represented as T sub 0. This T sub 0 is going to be your final temperature. And we can determine this from the equation of the line, where we know that the y-axis is representing the temperatures that you monitored. The x-axis values represent time. So we can input 0 for our time and solve for y, or t0, which is going to be our t final. So we're going to input this is equal to negative 0.8203 times x, which is our time of 0, plus 49.1. We know that anything multiplied by 0 is going to be 0. So what that means is that T sub 0, or the final temperature, is equal to 49.1 degrees Celsius. So now we can look at the change in temperature for our cold water and hot water respectively, where if we're looking at final temperature of 49.1 degrees Celsius minus the initial temperature of 24.0 degrees Celsius is going to give us a temperature change for the cold water of 25.1 degrees Celsius. And I'm going to highlight this in blue for ease of viewing the cold temperature, and then we'll do pink for our hot temperature. So again, our final is going to be 49.1 degrees Celsius for the hot water minus 78.0 degrees Celsius for our initial temperature for the hot water is equal to negative 28.9 degrees Celsius. And we're going to highlight this in pink to keep everything straight. Now we're able to input this information to our equation for the change in heat. So the change in heat for the cold water is equal to the specific heat, or 4.184 joules per gram times degrees Celsius, times the change in temperature for the cold water of 25.1 degrees Celsius, times the mass of the cold water sample, which was 50.0 grams. I always like to cancel units to make sure that we're on the right track. And so delta QC for the change in heat for the cold water is going to allow us to make sure that we have some sort of joules in our final answer, but going through and looking at what's in the denominator and in the numerator, we see grams. We also see delta C, or excuse me, degrees Celsius in the numerator and denominator. So we would be left with an answer in joules here. So to solve for the change in heat for the cold water, we need to multiply 4.184 times 25.1 times 50. And that is going to give us an answer of 5,245.9 joules. Now, you'll notice that the sign is positive here, which means that this is the heat that was absorbed by the cold water upon addition of the hot water. One other aspect here is that we need to consider the significant figures for a final answer if you were reporting this on an exam. So we see that there are 4 in our specific heat. Oops, we'll use the laser pointer. 4 in our specific heat, 3 in our temperature, and 3 in our mass. So we need to report this to 3 significant figures. We see that the following digit is a 5, so that will round up. And so if we're asked for the change in heat for the cold water, we would want to say, and we can use the roughly equal to sign as 5,250 joules for our heat of the cold water, change of heat for the cold water. in terms of continuing with calculations, we would want to use this number so that we avoid rounding errors. But what you report for sig figs, and keeping those sig figs in mind, would be 5,250 joules. Now I'm going to do the same approach for the hot water. So we'll say the specific heat is going to be multiplied by the change in temperature of negative 28.9 degrees Celsius times the 50 grams of hot water that were added to the cold water. Again, we can cancel units of grams and grams, degrees Celsius and degrees Celsius, so that we end up with negative 6,040.1 joules by multiplying 4.184, negative 28.9, and 50.0. We can also take a minute to evaluate significant figures here, where 28.9 or negative 28.9 and 50.0 each have 3. So we should report this 6,040 with 3. And so we're going to say that this is 6,040 joules if you're asked for the final change of heat for the hot water. Oops, and I've left off my negative sign over here, so we want to make sure that that sticks around. Okay, now these are the heat changes associated with the hot and cold water individually. We also want to look at the heat change of the calorimeter because our goal is to look at the heat capacity of that calorimeter. So the heat change of the calorimeter is equal to the change of heat for the hot plus the change of heat for the cold water, and taking the absolute value of that term. So when we do this math, we see that negative 6,040.1 joule plus 5,245.9 joules, and taking the absolute value of that term, is going to give us 794.2 joules for our change in heat for the calorimeter. And so now to get to the heat capacity, or capital C, of that calorimeter, the math that's going to be involved is taking this change of heat of the calorimeter and dividing that by the change in temperature of the calorimeter. Now you'll recall that in terms of the experiment, you initially had cold water in the calorimeter that you added hot water to. And you equilibrated that cold water so that it was matching the temperature of the calorimeter, essentially. And so what that means is that we're going to use the change in temperature for the cold water, or 25.1 degrees Celsius here, for our change of temperature for the calorimeter from the addition of hot water to cold water. So the setup for this is going to look like this, where we have 794.2 joules divided by our temperature change of 25.1 degrees Celsius is going to give us 31.6 joules per degree Celsius as our heat capacity for the calorimeter. And so that's our objective for activity 1. And you'll recall that you had 2 trials so that you can take the average heat capacity of the calorimeter. For example purposes, we're just working through this once. And then one other aspect here is making sure that we're reporting things with the appropriate significant figures. We are doing so in the case of the math for the heat capacity of the calorimeter, as well as, since we have 3 significant figures in our temperature here, we have 3 in our final answer. And so that's the heat capacity of the calorimeter. Now we're going to use that information for the sample calculation involved in activity 2, where activity 2 involved taking calcium chloride, and you used a known quantity of 5 grams, but there were other trials in which you used different masses of calcium chloride, and you added that to a known volume or known mass of water of 100 grams. And you monitored the temperature of the water before adding the calcium chloride, and upon adding the calcium chloride, you watched until the temperature stopped changing and recorded that steady value. So those are representing our initial before you added calcium chloride and final once it stopped changing upon addition of calcium chloride. A few other aspects that are represented here are the molecular weight of calcium chloride, which hopefully everybody knows how to calculate based on the atomic masses of calcium and chlorine. And then the heat capacity of the calorimeter was determined from activity 1. So I've just input that number here. And finally, our specific heat of water is that standard value again, but I want to make sure that it's viewed here so that we can follow that during our calculations. Now, the first goal here, the main goal here is to determine the enthalpy, change in enthalpy per mole of calcium chloride for this example. And so we're going to use a few calculations to get to that point, where the first one we're going to use is to interpret this change in temperature based on the final minus the initial. So inputting our final temperature of 31.0 degrees Celsius minus the initial of 24.0 degrees Celsius, that gives us a temperature change of 7.0 degrees Celsius. Now, we're going to use that in order to assess the heat, the change in heat associated with the absorption by the solution. So in your data table, this is abbreviated as the change of heat for the solution, or water here as the W, and that's equal to the negative product of the specific heat times the change in temperature times the mass, because we're talking about the heat absorbed by the solution. And so we're going to then input our specific heat. We've just calculated the change in temperature, and we have the mass of the water in our table for what we know. So we're going to do this math and say this is equal to the negative specific heat times the change in temperature times the mass of the water. And we can cancel units accordingly, grams and grams, degrees Celsius and degrees Celsius, so that our delta QW is going to be equal to negative 2,926 joules. And in terms of reporting based on sig figs, we see 4 here, 2 here, and 4 here. So that would give us an answer represented in 2 significant figures. So we can say that this is equal to negative 2,900 joules if you're reporting that on your exam for a final answer for the change in heat for the solution. Now we want to take a look at the heat absorbed by the calorimeter. So the change in heat for the calorimeter is going to be expressed as negative heat capacity of the calorimeter, heat capacity of the calorimeter times the change in temperature. So we have negative heat capacity of the calorimeter. We found from activity 1 is 31.6 joules per degree Celsius, and the change in temperature from the addition of calcium chloride is 7 degrees Celsius. So now we're going to indicate this math by making sure we cancel units first, degrees Celsius and degrees Celsius, so that we have our temperature change associated with the calorimeter, or heat change associated with the calorimeter, as 221 joules. And so again, bearing in mind significant figures, there's 3 here, 7 there. And so instead of having negative 221 joules, we would report this as negative 220 joules if needing to provide a final answer for the change of heat for the calorimeter. Now we're prepared to start looking at our change in enthalpy, or delta H. So delta H is going to be represented by the heat of the solution plus the heat of the calorimeter. And so again, we're going to use the initial values before rounding with sig figs to make sure that we don't have additional rounding errors that we assume in our calculation. And so this is going to be equal to negative 2,926 joules plus our negative, or minus 221 joules. And so this is going to be equal to negative 3,147.2 joules for delta H, or the change in enthalpy. If you're asked to, like you were on the data sheet, convert this from joules to kilojoules, I'll zoom out a little bit so that we can continue that here. We can multiply times 1,000 joules in 1 kilojoule. So essentially that's dividing by 1,000, and that will allow us then to cancel joules and joules, so that we have negative 3.1472 kilojoules. And then we want to ensure that we have the final answer in the appropriate expression of change in enthalpy per mole. So how are we going to incorporate our moles here? So our moles of calcium chloride are going to come from looking at the mass of calcium chloride and the molecular weight of calcium chloride, where we have 5.0 grams of CaCl2. We're going to divide by 110.98 grams in 1 mole, and that is going to give us 0.045 moles of CaCl2. Actually, there's another 0 that trails here, but we can represent that as 0.045 in terms of sig figs. And so what that will then allow us to do is calculate delta H per mole as negative 3.1472 kilojoules divided by 0.0450 moles of calcium chloride is going to be equal to negative 69.9 kilojoules per mole. Or if we take into account sig figs, and we had, if we had 2 from the original, we would report with as -70, but because we have, and when I say in the original, I'm talking about the number of moles here, we have 1, 2, 3, 4, 5 in our delta H here. In incorporating our moles without the rounding, we have 3. So that means we're at our appropriate 3 significant figures in our final answer there. And so that is how you can go through the calculations for the calorimetry experiment.